In this chapter, we've been focusing on the rotational equivalent quantities for linear quantities that we've discussed earlier in the year. We've looked at angular displacement, angular velocity, and angular acceleration, as well as torque, which is in some ways the angular or rotational equivalent to force. All of these quantities were things that were vectors, and so it likely makes sense that we have rotational equivalents for them. But in this video, we'll be introduced to the rotational equivalent of mass. That may seem a little odd because we have not yet talked about, or because mass is a scalar. And so it doesn't maybe make sense for it to have a rotational equivalent. So to understand why it has a rotational equivalent, let's talk about what exactly is mass. Earlier this year, we defined mass as being a measure of an object's inertia. Or a resistance to a change in its motion. Something that has more mass resists a change in its motion more. When you think of mass in that light, it may make a little more sense that we have a rotational equivalent. In other words, the rotational equivalent to mass, which is called the moment of inertia, or sometimes I abbreviate it to MOI for short, would be the object's resistance to a change in its rotational motion. So let's think about what would make an object easier to start moving, to start rotating, or maybe harder to make it start rotating. If you think about that idea, you might realize that this moment of inertia quantity might depend on an object's mass, it might depend on an object's shape, and it also might depend on where the mass is located. The moment of inertia is not a set quantity for every object, but rather follows along with a series of equations. For honors physics purposes, we will simply look up those equations on a chart that is either in your textbook or this chart can be found on your equation sheet. This chart gives some equations for the moment of inertia, which is represented by a capital letter I, according to certain geometries of our objects. So as you'll see here, a hoop or cylindrical shell goes with the equation mr squared, where m is the mass of our hoop and r is the radius of our hoop. If we have a solid sphere, then it's 2/5 mr squared. Again, m is the mass and r is the radius. If we have a solid cylinder or a disk, we use 1/2 mr squared. If it's a thin spherical shell, maybe something like a tennis ball or a basketball, that would be 2/3 mr squared. If it's a long, thin rod where our rotation axis is through the center, we'll use 1/12 ml squared. And a long, thin rod with the rotation axis through the end is 1/3 ml squared. Understanding where these equations come from requires calculus. That's something that you'll learn about if you choose to take AP Physics. But in the meantime, we'll need to use these equations. A couple of other facts about moment of inertia. Just like mass, you can add moments of inertia. So for example, if I have an object where I have a long, thin rod and two masses on either end, with my axis of rotation passing through the center, I would use the moment of inertia for the long, thin rod with the axis of rotation through its center. And then I'd also use values of the moment, or equations for the moment of inertia for the two masses on either end, and add all three of those together. That brings me to my next point. If your axis of rotation is far From your object's center of mass, we'll use the equation mr squared, regardless of what shape your object is. Now, far is a relative term, of course. For the sake of our class, far would mean that the axis of rotation is at least maybe 3 or more radii away from the center of mass. I'll try to make it obvious when it's far and when it's not. The next video, or the next thing we will learn, will introduce you to why the center of mass matters as we're using it in class.